Greetings. I am here today to introduce and explain and demonstrate a simulation that I wrote to show why we get planetary conjunctions, like the Great Conjunction a few days ago, of Jupiter and Saturn in late 2020. So to explain why they happen and to show why they happen so rarely. Um, so I want to start with an explanation of the physics behind what the simulation is doing. If you're really just interested in seeing the simulation, I would fast forward ahead until you see most of the screen go black, because the simulation is against a black background, so you can recognize when that starts. But if you want to know how it works, I'm going to try and explain that first of all. So the basic idea is that within the simulation, within the computer program, we're going to define a bunch of objects that within the program I call rocks, but it's just a name. You could call it anything. Um, and what the program's going to do is put these rocks at various locations, which is up to the user. If you copy this program yourself and play around with it, you can put the rocks wherever you want. Um, and it assigns each rock a mass. So I'm going to call this rock 1, 2, 3, 4 going in clockwise order. So we have a mass 2, a mass 3, and a mass 4. And it's going to give each one a position in space, and it's going to give each one a momentum. So maybe this one starts out going that way. Momentum is traditionally written with a P, I guess because M is taken with mass. But let's start each of these off with a momentum. The little arrow above it indicates that it has a direction. So maybe that's P1, and I don't know, let's have P2 going that way. Okay, so the basic idea is that momentum is equal to mass times velocity. So if I take that momentum and divide by the mass, that tells me the velocity that it's going at. And velocity is the rate of change of position. So if I take a small step in time, so small step in time, and let's call that dt. So dt might be a second, it might be a millisecond. It's a small step. But if you take the small step in time and you multiply it by the velocity, that tells you how much the position changed in that amount of time. Literally, just if you're going 50 miles an hour for 1 hour, you multiply the 50 miles an hour times the hour and you get 50 miles. You've gone 50 miles. So that's all it's doing. And it says that if I take the velocity, multiply by the dt, that tells me how far it moves. So that might be from this location to that location. And this one might move from this location to that location. But it's going to be along the same direction as the velocity, which is in the same direction as the momentum. And then I go another small step dt, and it'll move each mass along another step. And I go another step, and everything keeps moving. Each time one step dt into the future. Now, that alone would be kind of boring. Everything moves in a straight line. That's called Newton's first law. Everything moves in a straight line unless something acts on it. Bringing the acting in is where the physics comes in and where it gets interesting, because each of these masses is not alone in the universe. They affect each other, and they affect each other through gravity. So we have gravity, and each of these masses pulls on all the other masses due to gravity. So for example, M3 here is pulling M2 in that direction, it's pulling M1 in that direction, and it's pulling M4 in that direction. And then M4 is pulling on all the others. It's pulling M3 this way, it's pulling M2 that way, it's pulling M1 that way. If I'm not lining these up right, imagine the arrows are pointing toward the masses. Okay, and then M2 is pulling on the other three, so it's pulling this way, and this way, and this way. And then I think I have one more. Which ones have I done so far? M2 is pulling, M3 is pulling. I haven't done M1 yet. So I need one more color. Color I haven't done yet. Yellow, hard to see, but M1 is going to pull that way, and that way, and that way. So each of these masses is exerting a force on the other masses, and I can add up these arrows. So this one plus this one plus this one is going to be something kind of like that, and these are going to add up to be something kind of like that. These are going to add up to be something kind of like that, and these are going to add up to be something kind of like that. So those black arrows represent the total force on each object. So this would be F1, this would be F2, this would be F3, and they have directions, so I give them little arrows, and this would be F4. Now here's the key. Force is the rate of change of momentum. So I can do a similar game to what I did with velocity. I know that momentum 3 is pointing up here. I take the force and I multiply it by dt, and I get the change in momentum. So dp is equal to f dt, just like d position was equal to velocity dt. Same idea. So if I know that F3 is this way, then I know that P3 has to change in the direction of F3. So I would get a dP in this direction parallel to F3, and my new momentum would now be pointing this way. So the rock, and then I apply the position change. So the rock is going to not move up anymore. Now it's going to move slightly to the left. And similarly, this momentum is going to change in that direction. So this rock is going to slow down and curve slightly to the right. This momentum is almost aligned with the force. So this rock is going to speed up and go slightly to the right. And this rock is going to slow down and almost not change direction at all. So based on the forces, you get a bunch of changes of momentum. You change the momentum of each rock. You iterate to the next position based on the velocities of all these new velocities that come from the new momenta. And then you have new positions, so you recalculate all the forces based on the new positions. And Newton said that the force between two objects is going to be equal to the mass of one object times the mass of the other object divided by the distance between them squared, with a fudge factor out front to make the units work out. So, and then there's a direction. It's along the direction of the distance between them. So that's the fancy math. But the basic idea is you take each pair of masses, so like let's say M3 and M4, and you multiply the two masses together. You divide by the distance between them. This would be r34 squared. And then the direction, this would be in the direction of 4 to 3, and this would be in the direction of 3 to 4. So you switch the order of the numbers and it changes from a plus to a minus, so it goes the other way. And so you can see from the math that the force that 4 pulls on 3 is the same as the force that 3 pulls on 4. And that's Newton's third law, that for every action there's an equal and opposite reaction. So all of this is Newton. We're not bringing Einstein into this at all. We don't need him. Not for this. So that's the basic idea of what the simulation is going to do. So let's go to the simulation. And I believe you can see that now, but I want to be able to write on it. So let me do that. Okay. So the way I wrote the simulation, I have this thing here called God View, which basically lets me determine how I'm looking at the simulation. Am I looking down on it from above, so to speak, or am I on the Earth looking out at the solar system? So the God view, as I call it, is looking at it from above. And if I turn that to false, I'll get it from the point of view of the Earth. So let's start with the God view. And this is our fudge factor to get the forces to turn out right. And then I define a bunch of rocks. At the moment I have 4, the Sun, the Earth, Jupiter, and Saturn. And just to show you how it works, I'm going to go ahead and add a 5th. I'm going to put Mars in here just for fun. So I change my number of rocks up to 5. And then it's going to go through this line here, defines 5 rocks, and it just puts them all at the origin. It makes them all have a mass of 1, gives them all a radius of 0.3. I want to stress the radius here is not physical. If I made the radii proportional to the scale of the distance between these things in the solar system, you wouldn't be able to see them. So I made them all much too big. And then what I do here is just set those fake radii. So I'm going to add a 4th rock, or 5th rock, sorry. Starts counting from 0. So rock 4, that's the 5th rock. And this is Mars. Mars is about half the diameter of Earth. So I'm going to go ahead and make it proportional, and we'll see if it's even big enough to see. I may have to go back in and make it bigger. And then here I'm setting the mass. The mass of 1 is 1 solar mass. We're using units of solar masses, not kilograms. And we're using units of astronomical units for distance, which is the distance from the Sun to the Earth, 1 astronomical unit, not meters. And so I need to define all these things for Mars. Put them in. So Mars has about 1/10 of the mass of Earth. So I'm going to make that 10 to the minus 7 instead of minus 6. Got to change these up to 4. And what color should we make Mars? Duh, it's the red planet. And let's see, Mars's orbital inclination. I'll talk more about inclination later, but let's go ahead and put it in here, 854. And then its position. So I'm not trying to start these in realistic positions, except insofar as the distance from the Sun is accurate. And then the speed and the velocity, I want to put that, let's see, it's going to be going this way, and then yeah, that ought to do it. So if I run this program, it should give me um, the 5 objects. The sun will be at the middle, and there they are. And I clearly do not have Mars correctly. Look at that. So the Earth is going in a nice circular orbit. Mars obviously does not cross over the Earth's orbit, so I've got the wrong velocity for Mars. Let me go back and fix that. Um, oh yeah, I've given it Saturn speed, that's why. This should be Mars. Saturn is moving much slower, so if I have Mars moving that slow, it's going to fall in toward the sun. Let's try that again. That's much better, and except it's going the wrong way. So, once you have a simulation like this, you can use it to ask questions of the solar system, like what would it be like if a planet went the other way around? But they don't. They all go the same way around the sun because they formed out of the same clouds, so they all have the same angular momentum. Um, so I've clearly got Mars going the wrong way. I think I want it to go in the positive x direction. Let's try that again. There we go. That's much more like it. So I have the Earth, I have Mars, I have Jupiter, and I have Saturn. The little clock there that says time, that's counting off the years. So if you look carefully, you can see every time the Earth goes around once, it ticks up one number. So that's the time in years. And I've gone ahead and drawn, so you can see that it takes Mars a little bit longer to go around the sun than the Earth. It's going to take Jupiter about 12 years to go around, and it's going to take Saturn about 30 years to go around. And I've drawn arrows from the Earth to Jupiter and from the Earth to Saturn. And what you can see is that every so often the arrows cross over, like now, and then it takes a while for Jupiter to go around and catch up with Saturn again. But every time it does, you get a conjunction. So you can see they're going round and round and round. And here they come. And then right about now you get another conjunction, and you can see this one was about 45 or 65 years. The previous one was about 45 years. So it's about every 20 years Jupiter comes around and passes by Saturn on the sky. Now, you might be wondering, if this happens every 20 years, why is everybody talking about 400 years? It was 400 years ago that this last conjunction happened. And in fact, at that time, they were too close to the sun and nobody could see them. The last time that this happened where people could see it, like there it goes at 85, 84, almost 20 years. Last time this happened that anyone could see it was 800 years ago. So if it happens every 20 years, what's with the 400 years, 800 years thing? Well, from this viewpoint, it looks like all the planets are moving on a flat surface, like they're all rolling around on a table. But one of the nice things about this simulation is I can click and drag and rotate it around and look at it from the side, and you can see that they don't quite line up. They're slightly tilted. Now, those are realistic tilt numbers. One of the fun things about having a simulation is I can make those numbers unrealistic. So let's say, what if I put the Earth's inclination at 45 degrees? So now it looks like an ellipse instead of a circle like the others, but if I rotate, you can see that it's tilted relative to the others. And the Earth then is going up and down and up and down while everyone else is going around. So that's inclination. All the planets are mostly in the same line. Pluto is the biggest inclination of the traditional nine. Um, but let's put the Earth back where it's supposed to be. All of these inclination numbers are relative to the Earth, so the Earth gets 0. So what that means is that because they're tilted, they don't line up perfectly like they look like they do from above. So now I'm going to run this program from the point of view of the Earth, looking out at Jupiter. It's going to center the frame of the animation on Jupiter, take away the arrows, and you can see there's the sun whipping by every year. 3, 4. Here comes Saturn, and you'll notice that Saturn went above. Saturn went up here above Jupiter. I think Mars just went by. And when we get up to 25 years, Saturn will come back. Here it comes. And notice that it now went below Jupiter. And I think on this simulation, the third time through, it goes right behind Jupiter. But the point being that every 20 years, it comes around. And even though from above it looks like it crosses over Jupiter, if you're looking along the plane because of the tilt, each time around, it's going to be either closer or further away. You can see that one went like about there. So the third time through, it got closer to Jupiter than it did the other 2 times. And so every 400 years, we get a really close approach like we did this last Monday when you could see both planets in the same frame. Here it comes again. Not quite so close, a little bit further away this time. So with this program, you can watch this go over and over and over again if you feel like it. Now, once you have a program like this, so what I intended this to show was that every 20 years, you get the general direction to line up. Here it goes. This time it's below. But because of the tilt, each time it passes by every 20 years, sometimes it'll be closer, sometimes it'll be further away. And so the getting as close as it did this week, that doesn't happen very often. That's what happens every 400 years. Once you have a program like this, you can have a lot of fun with it. You can treat it as your own private universe and ask questions of it, like what would happen if the Earth was going faster? So I'm going to speed up the Earth here. In these units, the Earth's speed is 2 pi, but I'm going to make it 10% faster. And I'm going to go back to the God view from above. So if the Earth were going 10% faster, now you can see it makes a nice ellipse. It's not a circle. It's actually getting out to Mars's orbit. And if we wait long enough, they might line up so that they actually hit each other or perturb each other's motion. Oh, got close that time. This is actually more or less how NASA scientists figure out how to get from Earth to Mars. You give a satellite, a spacecraft, a boost so that it's going faster. It looks like the two hit each other, but remember, the sizes of these objects are greatly exaggerated so that you can see them. I should be able to zoom in. There we go. So if you make a satellite go basically 10% faster than the Earth, then you need to slow it down again when it gets out to Mars. And you also need to time it so that Mars is actually there when your satellite gets over there. And you can see this is going round and round and round. And we're getting some near misses, but we haven't hit it yet. One thing I want to stress about this program, it looks like the sun is staying put, but actually because the way I described it earlier with all the forces, all the objects are exerting forces on all the other objects, the sun is actually moving. If we zoom in inside the sun, you can see this yellow line here is a trail left behind by the movement of the sun largely because Jupiter is dragging on it. So that motion is all inside the sun, so you don't notice it. But when Jupiter is over here, it's going to pull the sun in that direction, and so the sun and Jupiter are kind of doing a dance around each other. We still haven't hit Mars, and we've gone around almost 100 times. So the lesson there is that if you actually want to get to another planet, you have to time your launch very carefully. But we can ask other questions like, you saw that Jupiter pulled on the sun a little bit. What would it be like if we made Jupiter much bigger? So, like, let's say instead of being 300 times the mass of the Earth, let's have Jupiter be the mass of the sun. And actually, since I start them all out at the mass of the sun, to get Jupiter to be the mass of the sun, all I have to do is tell the program to ignore that line. And now it's as if Jupiter is the mass of the sun. So that means we're essentially asking what would happen to the solar system if it was a binary star system. If we had two stars in the solar system, what would happen to the Earth? So now you can really see the sun is moving. Oh, Mars just got kicked out of the solar system. Bye, Mars. And there goes Saturn. The Earth seems to still be surviving. Nope, there goes the Earth. So you can see here Jupiter and the Sun are orbiting around each other in two nice ellipses. But Saturn, Mars, and the Earth were not stable. They got kicked out of the solar system. So if we were on Tatooine, we would have to be in a fairly far orbit. Oh, no, it looks like the Earth might be coming back. Yeah, the Earth is turning around. Saturn and Mars are not coming back, but the Earth didn't get quite enough energy to be flung out of the system. So if we were going to be on Tatooine, the only way you could get a stable orbit is to either be very close to one of the stars or very far away from both of them. Here comes the Earth. Got launched into a large orbit. And there it goes around again. Now that looks like it might not be coming back. So those are some of the fun things you can, and look, it looks like that passed by, perturbed the orbits a little bit. They got thicker here. Anyway, that's one of the questions you can ask of this kind of program. Another fun one is you can ask, what if gravity were different? These sorts of calculations. Now, Isaac Newton didn't have a computer. He did this by hand. But he knew from Kepler's work that the planets went in ellipses. And he looked at several different laws of how gravity might work. And he asked which ones would make ellipses. And he figured out that it had to be 1 over distance squared. So one thing we can do with this program is say, what would happen if it weren't 1 over distance squared? So right here, you can see this DISP mag2 is the computer's way of saying distance squared. If I take out the 2, that will give me just the distance. So instead of distance squared, we take 1 over distance. So that means gravity becomes much stronger. So how would the universe work if gravity were stronger? So these are definitely not ellipses. So this is what the solar system would be like if gravity were stronger. And because Newton knew that our solar system, the planets go in ellipses, he knew that 1 over distance couldn't be the right answer. It has to be 1 over distance squared. So we'll put that mag2 back in. So those are the kinds of things you can do with a program like this. You can add more objects. You can try to make it, there are ways it could be more accurate. Like obviously I could make the planets more proportionally sized, but then you couldn't see them. These orbits that I have here are too circular. Technically the orbits are ellipses, but they're very, very small ellipses. I could try and put in the actual eccentricity. Eccentricity is the word that describes how far off you are from being a circle. And on this scale, I don't think you'd even notice that it was technically an ellipse for any of these. They're very, very circular. But they are off from circularity enough that it can be measured. In fact, that's how Kepler figured out that they had to be ellipses, because he was watching Mars, and the eccentricity of Mars is about 5 times the eccentricity of Earth. But it's still small. It's still like less than 10%. It's just that the Earth is really, really circular. So this program was written in the Python language on a platform called GlowScript, and I will put a link to the program in the comments under the video. So if you want to go look at it and make a copy of it and play with it yourself, you are welcome to do so. Thank you for watching.